It's probably useful to go over types of forces and set some context here. First of all, a couple of statements just to get out on your radar. Force is a push or a pull, and so that's a pretty intuitive idea. We're going to quantify that idea. Secondly, force is a vector. Well, that simply means it has a magnitude and a direction. If you think about pushing something, the direction that you push with whatever magnitude of push you have is going to affect the result. So now, broadly speaking, there are two kinds of forces, non-contact forces and contact forces. So let's talk about non-contact forces first. Gravity. Conceptually, gravity is the attraction of one piece of matter for another piece of matter. And the gravitational force is pretty small unless the mass doing the attracting is fairly large. And so we are dominated, our lives are dominated by the gravitational force of Earth upon us. And so here I've shown you two objects, the Earth and the Moon. Um, and this is showing that the Earth is attracted by the Moon and the Moon is attracted by the Earth. This force is referred to as an attractive force, always tending to pull the two objects closer together. So we'll see this force is in terms of non-contact forces, the pretty much the only one we're going to be talking about in this quarter is going to be gravity, and it will have the label weight usually. Secondly, Coulomb force. This is the force between two stationary charged particles. Can be either attractive or repulsive, and just to show you two examples, if you have a plus and a minus sign, they attract each other. So I have them labeled 1 and 2. So there is an attractive force 1 exerts on 2, and then there's an attractive force that 2 exerts on 1. And as we'll talk about more later, the magnitude of these two forces is equal. Their direction is opposite. There's a second situation one can have with Coulomb forces on stationary charges, and that is if they are both the same sign. So here I've taken two plus charges. The same thing conceptually would happen if you had two minus charges, and in this case they repel each other. So I've drawn in the repulsive force of that particle 4 exerts on 3, and the repulsive force in the other direction that particle 3 exerts on 4. There are also magnetic forces, and I won't even draw pictures for these, but these have to do with forces a magnetic field has on moving charges and forces that one current can have on another, just as examples. Okay, so these are all non-contact because they are action at a distance, and so as you can see from the Earth and the Moon, there's no contact between these two. It happens in the empty space between them, and at least as far as we are going to think about it. Again, broadly speaking, there's another type of force, and those are contact forces, and for our purposes this means that something is touching the object that we're analyzing. And so just to very quickly go through these, and then I'll go back again, but there's a spring force, a tension force, a normal force, friction forces, drag forces, and thrust forces. So to start with spring forces, if you imagine a horizontal frictionless table with a mass attached to a spring, and the spring is neither compressed nor relaxed, so this is its natural length. If I take my finger and I push against leftward against the mass, I'm going to compress the spring. And if I immediately move my finger so that it's no longer part of this force paradigm, there will be a force of the spring on the mass that it's in such a way as to attempt to uncompress the spring. And similarly, if I stretch the spring, there will be a force of the spring on the mass that's in such a direction as to unstretch the spring. And it turns out, and we'll look at this later, that this force is, the magnitude of this force is, depends on two things. It depends on, first of all, on something called the spring constant via Hooke's law, and it also depends upon how much you stretch the spring. So given a spring with some constant K, if you stretch the spring twice as far or compress it twice as far, the force the spring exerts is doubled. It's proportional to how much you either stretch or compress the string. Second force, tension. And so here I have a simple picture of a mass hanging in the Earth's gravitational field, and of course it thereby has a non-contact force of the Earth on it. That would be this right here acting on this mass, pulling it down. But then there is the upward tension force of the string acting upward along the string, and the mechanism for that is you can think of the string as being made up of um, very tiny atomic springs, and as the springs get stretched, as these little atomic strings get stretched, it behaves somewhat like the macroscopic spring that we describe here. Normal force turns out is somewhat similar to both of these forces, but it is the force that comes about if you, for example, put a book on a level table. The force of the Earth will be pulling the table downward. That's a non-contact force, but then the table will be pushing back up on the book, and that comes about because, again, we can think of the table as being made up of many microscopic springs, and they are being compressed down by the weight of the book, and any spring that's compressed is going to push back up again. That's where the normal force comes from physically. And the physics is that it acts perpendicular to itself. Now it turns out there's two forces that a surface can exert on another body, and that one of them is the normal force perpendicular to the surface, the other one is friction that is parallel to the surface and in such a direction as to oppose the motion for the most part. We'll talk about this in more detail later. Then there's drag, and drag is what makes a parachute work here. And so, believe it or not, this is a drawing of a mass attached to a parachute, which is going in the downward direction. And what the function of the parachute in this particular scenario is to arrest the downward acceleration of the mass so that it achieves what is known as terminal velocity, and it does that by having relatively large mass and therefore weight, as we'll see later, to produce an upward force on whatever it's attached to, or on itself, as far as that goes. So it acts, drag acts opposite to the motion. So if the parachute was moving down, the drag force would be up, and it's caused essentially by air molecules hitting the surface of the object. In this case, the parachute would be impacted, the bottom surface would be impacted by air molecules, since it is moving down relative to them, and on the average these air molecules are not moving. Finally, there is the force of thrust. So here I've drawn a little rocket with the rocket motor flame symbolizing the expelled fuel that's coming out the back, and if the fuel comes out the back, there is a force. Easiest way to explain this is with conservation of momentum, which we'll meet up with in several weeks, is opposite the direction that the expelled fuel is coming, and so this would be upward. So okay, so let's move ahead now and talk about some of the ways of identifying forces and then using Newton's laws to predict what the motion will be, because that's what mechanics is all about.